I didn't do anything for this class while we were out, so you didn't miss anything. My Wi-Fi is still down, so for me to like make a recording, I'd have to go somewhere to do that. I just didn't do it. Yeah.
Was your Wi-Fi up for like 10 minutes?
No, my Wi-Fi was up for like 6 hours.
And then, so you emailed us, did it, and then it went back down?
No, I can email from my phone. I'm just not gonna try and make a recording from my phone. But it's funny because it came up, we're all excited. I made a lecture for another class, and then I went outside and did some more like maintenance in my house that took quite an impact. Thinking I had Wi-Fi back, and then I came back in to do more and it was gone. But there's so many of you that didn't have access that it really didn't make sense to do a whole lot of production. Half of you would have got it, half of you wouldn't have, and I would have had to start over anyway. So I was like, we're just gonna lose a week. A week in this class is fine. I'll do a couple topics today, so we'll start to catch up right away. But yeah, a week in this class is okay. There's other classes that I still haven't figured out how to catch up, but I thought we'd start with a couple things. I like current events, and we just had one, right? So anyone have any trees go down? Yeah. Why are they going down? I mean, these are trees that have been up forever, right? What'd you say? Why are they going down? Somebody said something. The weight. So, okay. So trees are typically like this, right? I'll just give you a fir tree. So first of all, what holds the tree up? The roots. And what do the roots look like on a fir tree? Anyone know? They go out as wide as the branches typically. If you didn't know that, that's true. So the roots are going to go out into here, right? And they're going to go all the way around, and they're going to give the tree some stability. That makes sense? So the weight comes down. Let's say it ices up. And ice is pretty heavy. It's about 2.5 times heavier than snow. So just think like an inch and a half of ice is like 2.5, 3 inches of snow. And then there's some variety there because there's super wet snow and there's super dry snow, but that's just in general, right? So yeah, it gets a bunch of weight on it, but if this tree has grown normally, right? All that weight acts how? How does that weight act? Down, vertically downward. Weight always acts vertically downward. So the branches get heavy, they might break off, but what takes the tree down? Why does the tree fall? Yeah. The wind can do it for sure. So if the wind blows, what's that do to the tree? The tree does this a little bit, kind of leans off to the side. And now we're doing what? We're asymmetrically loading the tree. Symmetrically loaded would mean it's all coming down, right? Asymmetric means we have now load off to the side and the tree could fall over. It could break, but most of them don't break. And if they do, they break up kind of high. The top breaks off, right? But if the tree's actually going to go over, then how does it go? Like what gives up? The roots. Not normally. The root wad stays intact. So usually the roots, they hang on, but what happens? Yeah, the soil gives up. So the soil pressure. So if we're leaning off to this side and our weight's over here, this thing wants to go this way, these are really holding on, right? And they put a big bunch of web of roots out, but those roots are in soil. And if that soil is normal, it's about 1,500 PSF. What's PSF stand for? Just take it, pounds per square foot. Yep, PSF, pounds per square foot. Normal soil pressures in our area, 1,500. If you get a wet area, you might be down as low as 700 PSF, right? So a little bit of wetness, if we have soaked soil, and then we get some kind of event, we get a little bit of wind, that soil can't hold it anymore, and it gives up. So the soil pressure is what typically holds the tree up. Okay, same thing with our buildings. Soil pressure. We build our buildings on the ground, right? And yeah, we put a lot of concrete down, especially here at the college. We put some extra concrete down. But what's under the concrete? Soil. Soil pressure is what keeps things in vertical condition. So trees, they have a tougher time because maybe the tree's not vertical, maybe the tree, maybe we have a slope and now we have a tree, right? And that tree and the slope has slid. If that happens at all, then the tree grows like this. And then those will go over even easier because when they get asymmetrically loaded and a little bit of wind, boom, they're gone. Okay. But yeah, it happens to buildings too. All the time we see structures with flat shed roofs and they get some kind of a ice and snow event on them and they can collapse because they're just not going to shed any of this load. All that load's going to come down. And we have certain codes for loading, right? Anyone know our snow load in this area? So if I'm going to design a structure in this area, I have to know the snow load because when it snows, that 100-year snow event, I have to design for that. Okay. It's 25 in Gresham, PSF. That's just snow. So we would add on an ice load. The ice load is usually only additional 5 PSF. And then if it's a vertical thing, or if we're working with shear, then I would have to add a wind load. But just snow load is 25 pounds per square foot. Okay. So you can look up the density of snow. It's about, what did I find when I looked it up? 20 pounds per cubic foot is a typical snow load, right? So you can do the correlation. What's your guess on the snow load at, this is Gresham, right? What's your guess on the snow load at government camp? Because we have a lot of structures in government camp.
35.
35, I hear 35. Anyone else want to guess? 30. Come on, guess. 40. It's 300. Yeah. Yeah. So if you're looking at 10, 12, 15 feet of snow on a structure, it goes dramatically up. Yeah.
So how much extra materials does, like, if you're building a government camp compared to Gresham, how much extra materials do you think you would?
So I've never built in government camp. I've built in Welch's, which is 1,500 square feet, 1,600 square feet, and it's 50 pounds per square foot for the snow load. So not a lot different than here. It's not that much higher type of thing. You don't need a lot more materials. You just need more massive material, right? So what you can get away with here in Gresham, Portland, this area, kind of a rule of thumb. If you're going to use a 2x6, and everyone know what a 2x6 is? Piece of wood, a piece of lumber, right? How big is a 2x6? Is it 2 inches by 6 inches? No, that'd be too easy. It's 5.5 by 1.5, and it varies 1 3/4 depending on the lumber that you get, right? So this is a 2x6, 2 inches by 6 inches. The typical span that you can put a 2x6, a rule of thumb, you can't use it everywhere, is 6 feet. So if it's a 2x6, you can span 6 feet. Does that make sense? Span meaning how far you can, put the supports. 2x8, 8 feet. 2x10, 10 feet. So you go to Welch's, that doesn't work. 2x6 can go about 3 feet. You go to government camp, 2x6 is not even on the list. You're not even going to use that thing. It might be a 4x8, 4x10 for floor joists or rafters or anything else that's going to carry snow load. Anyway, good. All right, a little current event. Any questions about our first week? That was so long ago. We did the academic plan, right? I think most of you got it in, but not all of you. So I'm going to let you still get it in. If you want to get it in. I did zero it in the grades. So if you look into the grades, you'll see that that's been zeroed. And that's it. That's all we've done. So this week, you'll have a lab that's homework that'll be due Thursday. And it's on graphics, which is the second set of slides that I'm gonna work my way through, but it's this assignment. It's up on Blackboard. I wanna first talk about teamwork. So we have certain topics that we have to cover in this class. This is introduction to engineering, right? Intro to engineering. So engineers work in teams and you're gonna work in teams in the project. So I like to cover a few things and give you some skills, I guess, to work as a team and also understand how engineering teams work. So let's take a second. We will have a notebook check Thursday, so that's a heads up. You should have a notebook going. You don't have to have the notebook with you, but whatever notes you take should be in the notebook. That's also my way to verify you were here. If you're not here and you can listen to the recording, then you can do the notebook still. And if you're not here and you can't listen to the recording, you can give it with somebody else and get the notes still. So you have many options to get it. But take a minute and write down, we've all had team experiences. We've all had helping behaviors in teams and hindering behaviors. That's the next slide, hindering. So you can make a little 1 column, 2 column. And from your experience, write down what helps teams and what hinders teams. And I'm thinking you'll be in a team of 3. So we're not talking a team of 25. Like we have at Mount Hood Ski Patrol. We're talking about a team of 3. Helping behaviors and also hindering behaviors. 2 minutes. Or 3 minutes. All right, let's stay positive first. Helping behaviors. Somebody offer up a good helping behavior. Gina. Communication. What kind of communication?
Like, talking about who's gonna do what and-
So verbal communication, that is helpful. What other kind of communication is helpful? Yeah, so email. So email communication that's helpful is what? It's timely, it's concise, it's not rude because it's so easy to be rude in email, right? It's not like we're face to face. I can tell you you stink via email much easier than I can do that in person, right? So be careful with that. All right, good. What are their good helping behaviors?
Contributing to the team, even if it's just an idea.
Absolutely. Like participation, contribution, right? That is helpful. Evan. Leadership. So I'll talk about successful teams in engineering in a second, but leadership is actually a big part of it. Successful teams have good leadership.
Next to each other.
Like for sure. Absolutely. Being kind to people, being respectful, all of those things. Yeah. Yep. Yep. You're a team, right? So we should be building each other up, not the opposite. Accountability. If you're going to say you're going to do something, do it. Yeah, that's great. Excellent. All right, let's go a little negative here. We've all had these experiences, right? So let's just talk about them. We'll get them in the open. When you get broke into teams, we're going to revisit this. You're going to revisit this as a team. Gina. Procrastination. So yeah, if I said who procrastinates and everyone didn't put their hand up, I'd be surprised. We all can do that, right? Really hurts a team though. Like it hurts you like in your own life. But when it comes to teamwork, it really hurts. What else? What other hindering behavior?
Not communicating.
Yeah, the opposite of the good ones, right? Yeah, I almost went down that path. Yeah,
Doing all your work through the groupmates.
yeah, just not participating, not doing your share, letting other people do the work.
Like low effort, like when you do have your job, just get it done. And all.
Yep, low effort, low energy is a big pet peeve of mine. Like when teams get together and somebody says, man, I'm super tired and just really exhausted. It's like, wow, how to bring a team meeting down in the trash can immediately, right? So suck it up. If you got low energy, well, don't bring that to the team. Bring high energy and then do low energy on your own, right? So yeah, I have a real issue with that. So I'm tired all the time, just so you know. But I'm not going to come in and say, oh, I'm super tired. Boy, that'd be a downer in class, wouldn't it? Your instructor comes in and says, man, I'm beat. I'm no fun. That's what I'm saying. All right, what else have you experienced? Yeah, exactly. Good. So the thing is, what I do this every term with GE101, right? And you all just run through the list just fine. Because you all know what helps a team and what hinders a team, yet some of this will happen this term. Happened last term. I had 8 teams. One team had like 2 non-performers. So I'll kind of get into my soapbox at some point about high performers and low performers and then non-performers, right? So I'm a baseball coach, and in baseball, we talk about players. Some players watch what's going on. You don't want a baseball player just watching, right? But some students in engineering just watch, like they're just observers. Other players in baseball make things happen, right? And other students in engineering, they make things happen. And then there's the other student that just wonders what's happening. Like I have baseball players that are like, what's happening? They're standing there, right? Watching everyone throw the ball around and like, what's happening? Like, whoa, that's not good. Right? And there's engineering students that like walk in and go, wow, what's happening in this class? Like they don't know. I'm like, oh, geez, come on. So high performers is what we're looking for. And you can be a high performer, you just have to choose to be one, right? We all can be high performers. So that really helps a team. All right, let's look at what successful teams, this would be what the research shows. Get this out of the way. So common goal. So one of the first things I'll have you do when you get in the term project, we're not in it yet. We will not be in it Thursday. You will be in it next week, right? But when we get in the term long project, one of the first things I make teams do is write a problem definition. Like, what is the problem you're trying to define? That's so the whole team can rally around the common goal. It's remarkable how many teams I'm involved with. I'll meet with that team. This is on my kind of side engineering projects. I'll meet with the architect, the structural engineer, and myself. All three of us will meet. And we're not on the same page. I'm like, how could we not all be trying to solve the same problem? I don't say that, but I'm wondering that, like, what is the architect doing? Like, we're not even solving that problem, right? So common goal is huge, and everyone understands the common goal, and everyone understands the scope of the common goal. Okay. Next. Uh-oh, it's stuck. Pretty sure there's more. Oh, there it is. Leadership, somebody mentioned that. So you may choose your team style when we get into the bigger project. Successful teams in engineering typically have not just leadership, good leadership. So maybe a manager, right? An engineering manager. Unique contributions, I think that was mentioned. So everyone has a different background. Everyone has the ability to make a unique contribution, whether that's my graphic skills or my design skills or my writing skills or my management, organizational skills. You know, we all have our opportunity to make our unique contribution. Effective communication, you guys got that one. Excitement, I got that one, but I think you were all heading down that path as far as like being kind, just the whole mindset as you're walking into a team meeting or a team project. And so back to this, you don't get to choose the project in this class, I choose it. And guess what? When you get to work, you don't get to choose the project, they choose it. So it's like going to writing class and getting excited about it. That's difficult for me. Yeah, somebody's shaking their head, no. But honestly, that class will go better if you generate a little excitement for your writing class. It's just gonna go better. It's gonna be like spreading through the class. So anyway, think about that. Respectful of each other, you guys got that. A plan, super good for successful teams. So we will develop that when you do your team formation paper. After you get into your big project, you'll do this, right? You will go through some of this stuff. I'll make you do it. All right. So I like this. I saw this a long time ago. Really, teams go down to the basic level of kindergarten. Like if you can behave well in kindergarten, you will behave well in a team, an engineering team. So it's simple stuff. So one of my really fun stories is I was pretty new at the college and I was put on, we have to do committee work here, right? So I'm on a committee with a bunch of other faculty. I'm a new faculty and I'm just trying to blend in, right? So the first few meetings, I just had M&Ms and I brought them. And it's like changed the whole mood of those meetings. Just bringing a big bag of M&Ms and set them on the table. I had to bring them every time then after I started doing it. But it literally changes the vibe in a meeting if you can start with something positive, regardless of what you're talking about. So the warm cookies and milk is kind of that part. Yeah, I don't know. I'm not going to talk about that. But it's nice if everyone just does that.
Do you have a personal experience with don't get people?
So one of my, I wasn't going to go, I like telling stories. This is a good story class, as long as I get through my stuff, right? So one of my later meetings, we have department meetings where all the engineering faculty get together with some science faculty and math faculty. And there was a gentleman here that I think just was having a bad life. Like a really bad life. Like I think his wife passed away, but I didn't know him that well, right? But he was just an angry human. So in the meetings, when he would object, and you'll find this behavior out there, he would get pissed, which is really hard to like work with, right? When somebody is like gets angry, and then he would literally like yell maybe and then leave, which just shuts down whatever conversation we're trying to have. But that was his response to conflict, basically. Or does someone disagree with him? You get pissed off and leave. Like, well, it's hard to like get past the disagreement though when he does that. It was a little bit effective because then that whatever that was just kept going. But that was here, right? Where I expect faculty to kind of act like professionals. Yeah, that was here. So I felt like he was gonna hit me one time. It was scary. Anyway, he decided to quit at some point and move on. He was having a bad life. Yeah. All right. Each team member should. I'm gonna blow through these because I want to do graphics. Stay focused. So, team meetings are tough and you'll go through a few team meetings. I make you do it, right? And then you'll meet outside of class, those kind of things. And it's hard for people to stay focused because, you know, there's fun stuff going on in life and Instagram and Snap, Facebook, and all those cool things are more fun than the team meetings sometimes. So it's staying focused is very, very helpful. Keep your meetings short is also helpful, folks. Don't do like drag it on. Help build the team. That was mentioned. Communicate, been mentioned a lot. So I will make you define your communication style within your team, which is what I do with my teams. So we're going to communicate how? Via email, maybe, right? Well, I know that's kind of old school, but that is a lot of engineering is done via email. But that's not enough. I need to know how often you will communicate via email if you're on my team. Is it a 24-hour response? Is it a 8-hour response? Should I expect a response in 5 minutes? Probably not, right? But you've got to figure that out within your group. So it's got to be a quick enough response that we have the information and we can get something done. But it has to be realistic, right? And there should be more than one mode. So whether that's text or Snap or whatever. Yeah.
When send email, can we put it in the school email or do we have to do personal?
No, you can do it via school email. Yeah, for sure. Positive environment. Keep it positive. Work hard for your team. Be patient with people. We do have lives that are going on, so be patient with people. You will have non-performers that show up in teams. That happens. There can be a lot of reasons for it, though. There can actually be legitimate reasons. And you don't know why somebody's a non-performer. They might not be telling you. So what that tells me is my performance is going to have to go up. And that's teams, folks. If a project deadline is next week and I have a team member not communicating, not performing, the project deadline is still next week and I need to get it done. I'll get it done to the best of my ability. It'll be on me. Yep, I had to do extra work. Yep, it's the way it is, unfortunately. Hopefully that doesn't happen in any teams, but it happens all the time. It happens in industry. It happens in this class. And you don't know why always, so don't make those expectations. Don't expect perfection from your team members. But you do expect certain things and you will set up that kind of organization early in the project. Document will be created, you'll all sign it and agree to it. And then we'll reference it if we have to, right? If we have a non-performer, we'll go back to that document. It's you signed it. You said you were going to do this and you're not. So, all right. Questions? That sound good? All right. Sounds good to me. Team roles. Oh, that's weird. Is it gonna, I wonder if it's gonna progress. Here, I'll put them up. So these are just some that come from industry. Project manager, engineering design manager, accommodation manager, service advisor, manufacturing technical expert, acquisition specialist, that's someone who gets the materials. Documentation specialist, that's someone who writes or does graphics specialist, right? We can have all different kinds of team roles. What are some team roles that you can think of that we could do in this academic setting? You are going to have to do graphics. You're going to have to do a structural analysis on the project. You're going to have to write some papers. You're going to have to do some documentation of results. We could have all kinds of team roles, right? We do want to divide and conquer. There's 3 of us or 4 of us, right? We don't all want to do the same work. We want to divide it up and work smart. Whatever work you do needs to be shared within your team because you're all going to be evaluated on that work. So if somebody else is doing graphics, I need to see that graphics so I can say, yep, I think that's what Troy wants because I'm kind of the guy, right? You're delivering it to me. You're trying to figure out what I want. But you need your eyes on it to say, no, that's not what he wants. He did not, he wanted this, right? So you still need to see everything that gets submitted because it's your work too. The teamwork is your work. So there needs to be a good system of getting stuff done fairly early to where people can look at it. If it's getting done last second, then it just gets submitted. The whole team doesn't see it. That's not a good scenario. You lose some points and people are pissed because you lost points and they didn't get to see it before it went in. It's not a good vibe. Some more just tossed out there. Theorist, the tinkerer, the computer person, the literature researcher, right? Again, you're not going to have all these roles, but these are some roles that come into industry. These are probably closer to the ones you're going to be working with. When I was with Kiewit, I was the design engineer. The materials manager was in the office next to me. The construction engineer, there was fabricators, right? They were out in the shop floor. There were construction engineers that were on site that then came to the facility looking for specific equipment that I had to work with. And then we definitely had a scheduling manager, which was our boss and his office assistant. So those are good roles for a team. All right, I'm not going to do ideation. We'll do that next. Design loop, we'll do that on Thursday briefly before our lab. But I want to talk about graphics before you get out of here. So this is the design loop. I'm going to make you follow this, but I'll talk about it more in detail later. All right. Let's see here. Who currently has GE115, which is the AutoCAD class? Show of hands. Oh, there's only a couple of you. That's good. This was covered in the AutoCAD class, so this is redundant for anyone who has engineering graphics. We start with this concept of orthographic projection. If you've never seen it before, then I need to show it to you because you're going to have to do graphics on your project. We work with graphics a lot, right, in the engineering world. So you should become aware of at least orthographic projection, the concept of it. Okay, so this is going to be your lab today. You're going to do a little homework set on this. So try to follow along and ask questions if you're not sure what the heck's going on. It's our way of documenting and sharing information, right? Spatial information. So whether that's a building or a widget, a part, doesn't matter. We do it the same way. Every industry does it a little differently. So civil engineers might do it a little differently than mechanical engineers. And then chemical engineers or electrical engineers would do it different again. It's just a different drawing standard, right? So the American National Standards Institute, ANSI, is the one that sets up all this code, standard code for drawing. So I'm going to give you just a few of them that I don't want you to break, few rules I don't want you to break, and that would be given to us from the American National Standards Institute, okay? So these aren't Troy's rules, these are engineering rules, and it allows us to share drawings. So when I send a drawing off to Intel, they get it, they look at it and they go, oh, I understand this because it's all to code. It's all to our standard, right? They send me a drawing, I look at it, I go, oh, I get that. I understand that symbology, I understand those dimensions, I understand that layout, right? It's so we can exchange drawings and everything looks similar. Not exactly the same, but similar, okay? So orthographic projection, I'm just gonna skip along, is where we take an object and we look at specific views. Ortho means 90 degrees, okay? So probably the easiest way to conceptualize this is actually with a 3D object, these 3D objects, and how we're pulling off a view perfectly 90 degrees to one side or the other, right? When we do an orthographic drawing, it's a two-dimensional drawing. It's not a three-dimensional drawing, but it's usually of a three-dimensional object, right? Does that make sense? So here's our object, and then here's this glass box that you can put around the object, and then you can look through one side of the glass box and get a view. That's what we want to do. That's our puzzle that we're trying to put together. The three primary views that I'm going to focus on and I'm going to want is the front view, the right side view, and the top view. Okay. There are more, right? There's the bottom and the left-hand side. So there's more than three primary views, but these are the three, front, top, and right side, that we typically almost always have. Almost always. Meaning that if it's a three-dimensional object, it's going to have those three views for sure. If it's a very simple three-dimensional object, like a piece of pipe is going to look the same from the front and the top. It's just going to be a rectangle, right? So we would not do all three views on something like that. But most things are complicated enough to where we're going to pull off these views. Okay? If it's a dashed line, see there's dashed lines in this right side view. That is geometry that we cannot see, but is there. It's hidden. Those are called hidden lines. So we want to represent hidden geometry, but we just use a different line type. We use a hidden line. These solid continuous lines are visible lines or visible edges of the object. So an edge makes a line. Even if it's not a 90-degree edge like this line right here or this edge, that creates a line in the front view, this thing, where this surface goes away from the front view. Okay, so if there's an edge or a surface change, it produces a line. It's a continuous line if you can see it. It's a hidden line if you can't see it. Like on this side, what are these hidden lines representing? The not circle, the hole. The hole. In the right side view, you can't see the hole. So we put in the top of the hole and the bottom of the hole as a hidden line. That make sense? What about the top view? What are those? The hole. Yeah, same thing. Yep. And then where do we see the hole in circular form? Front view, right? So the front view is the best visual description of the hole. Wouldn't you agree? It looks like a hole in the front view. That's where it should be dimensioned. That's where you should call out its size and its location, where it is best seen by all of us, right? So that's one of your first rules for dimensioning is you want to dimension where it is the most obvious thing that you're dimensioning. So if you're going to dimension the hole, call out its radius or diameter, you would do it in the front view because that's where it looks like a hole. Oh, whoops. Over here, it doesn't look like a hole, it just looks like a couple hidden lines, right? And up here, that doesn't look like a hole. I know it's a hole because my brain is putting the three views together. But here's where it looks like a hole. What about this sloped surface? See it here? That's it right here, right? Can I tell from this view that that's a sloped surface? No. What about this view? That's it right here, isn't it? This sloped surface? Yeah, but I can't tell. Where do I see the actual kind of slope cutback? Top view. That's where you should dimension it, in the top view. Does that make sense? All right. We're going to work on making front, top, and side views. Notice they're in projection. We call it in projection. The front view's here. The bottom of the front view lines up with the bottom of the right side view. That's called projection. The hole, if I projected the top of the hole over, it goes right to that hidden geometry. Same with the bottom of the hole over, right to that hidden geometry. The top of the arc projects over to the top of the right side. That's called projection. We want the front, the right side, and the top in projection of each other. Looks like this. When you get it done. It's a different object, right? But we see the front view projects up to the top view. In other words, this edge lines up with this edge. This edge lines up with this edge. Does that make sense? You don't put the projection lines in, but they're there. Yeah. Same with the bottom here, over and over. Of course, the right and the top, they don't project to each other. But that's the organization we're looking for. Front, right, top. Good so far? All right, let's talk about dimensioning just a bit. We're doing good. In graphics, you get this for a few weeks. In GE101, you get it for a few minutes. Okay. Dimensioning. Notice that all the text is one direction. It's called unidirectional text. It's all horizontal. That's mechanical engineering. Civil engineering will rotate these verticals and it'll put the text kind of, up and down. So that's just a different standard for a different set of drawings. Civil engineering is more construction, land development. Mechanical is more parts and widgets and things, right? So we're going to go unidirectional because I like it. I get to be in charge. And I'm a mechanical engineer, so it's my habit. Your goal is full shape description and full location. That's your goal. Full shape description. In other words, if I give it to somebody else, could they make it? Do they have enough information to make it? Okay, we don't want too much information. Like, notice the 79 is here, right? And it's not down here again. So we don't put the 79 here and also up there. That would be redundant. Oh. So we don't want redundant. We just want it in one spot. We want it in the best spot, the most descriptive. So none of them will look the same. We're all going to do it different. That's okay. Right? It's just fine. You can look at somebody else's and go, oh, that's a good way to do it. Right? We want to kind of cluster them. So 14 and the 40, like these two are what? Location. Locating the hole. So the hole's got to be located for somebody to put it in, right? So we have location dimensions. We have size dimensions. What's that? Probably a diameter, but they should have put it on there. Diameter or radius, one or the other, right? But that's the size of the hole, correct? Yeah, that's called a leader. Leaders are nice because you can kind of sneak them in anywhere. right? You can just find a little spot to sneak it in. Smaller dimensions go first, larger dimensions go next, and then even larger dimensions, if there was another one, like maybe the 50 could have been over here, then you would just stack them. There's a standard for that, but just keep it relatively close, right, to your drawing, but not jammed in there and not a mile away. This is called a dimension line because it holds the dimension. Right? There's a rule that we just don't cross those. So you can't just run an extension line right through. You can't just go like the 22 cannot be out here because the extension line would go right through the dimension. So these dimension lines are kind of sacred. Like, don't cut them up with things. Somebody's trying to read this drawing and we don't want 4 lines going through and have them try and figure out where the 94 is. We want it nice and clean, just like that. So many mistakes get made during the manufacturing process, and it can be because they just misread the drawing. They're working fast. They're going to read your drawing. If you have a bunch of lines going through here, they could read the 94 as to some spot here instead of here. All kinds of weird mistakes get made. So the cleaner you can make it, the easier it is for somebody else. So dimension lines, don't cross them. Extension lines can cross other extension lines, and they can cross visible lines, and they can be center lines, right? Here's an extension line, there's a center line. So extension lines need to go to whatever they're marking. Go to it. Like the 22 is marking here to here, this extension line goes to it, and then there's a comfortable gap. I call it a comfortable gap. It's supposed to be the same as the text height if you want to know the standard. There's a standard for everything because we did this by hand for a while, for a long while. And then CAD came, right? So we did it by hand in the beginning. All right, questions? There's a lot of rules there. You'll break some of them, that's all right.
Is the homework assignment for the orthographic projection, is it gonna be the same one as the one you did?
No, it's a little different. Yep. I had to make it different. I wouldn't want you doing the same one. Yeah.
I was gonna see if I could find.
Good luck with that. It's different. All right. Anything missing? It's supposed to be full shape description. Could you build that? Yeah. So Gina's talking about like which dimension?
Like the one on top, like just that one little
Yeah.
area.
So do we know how big this slot is? It's 10 by what? How tall is it?
It should be 10, but you'd have to do.
It's not there, right? There's a missing dimension there. Could you figure it out? Yeah, how do you figure it out? 50 and the 40, right? You got to do math. So here's the deal. We're the engineer. We're supposed to do the math. You don't want to hand this to somebody else and say, hey, do a bunch of math to figure out the drawing. Because they're going to muck it up. And then they're going to come back to you and say, why didn't you have this dimensioned appropriately? So there's a missing dimension. It should be this dimension. And this should be 10 because we don't want other people to have to do the math. We want to do the math. We are the engineers. We're supposed to do the math, right? So try to get everything on and don't have anyone else do the mathematics. Yes, it's a little redundant because you got the 50 and the 40, but trust me, you don't want to leave that to somebody else calculating out 10 from 50 and 40 because it can get screwed up big time. So it's a good rule to follow. Don't build in math work for somebody else when you're doing your drawing. Just do it all. Put it all on there for them. Make it clear. Okay. All right. This is not that one. Let's see. Let's look at it. This one is what you're going to do. All right. So you're going to take a piece of paper. There's white paper around here. If you want to use a ruler, you can take a ruler with you if you want. They're in the box back there. You're going to do a hand drawing and you're going to try to make the front, top, and side view. Okay? Yeah. And this is due Thursday. Yeah, we have a quick turnaround thanks to the ice storm. Yep, you're gonna want to get this done. You're gonna give it to me on Thursday's lab. So you got to figure out what the front view looks like, the right side and the top, right? So how do you know how big this thing is? Yeah, it has a little grid scale up there. It says the grid is equal to what? 10 inches. So every one of these squares is 10 inches by 10 inches. It's a big object, right? How overall length is 10, 20, 30, 40, 50, 60, 70, 80 inches long. Yeah, understand? All right.
Right side view, go over the drawing.
Yep. Yeah, I just want the front, top, and right side. Yep. So you got to figure out a scale to get it down onto this piece of paper. Because 80 inches, folks, is not going to fit on here, right? Agreed? So if we did 1 to 10 scale, that's 10 times reduction. 80 inches would be what? 8 inches. Still not going to fit, just so you know. So you got to figure out your scale first. That's the first thing to do. You got to get 3 views on here. Front, top, right side view. It's got to fit. Figure out your scale before you start. Leave enough room for dimensions. I didn't mention the title block, so make sure your name's on your paper. I didn't mention a title block. I'm not going to make you go there for GE101. Yeah. We're week 3. Week 2 is going to be a big blank. Thank you. Good question.
Can we use the yellow paper or the white?
Can we use yellow? What yellow?
Sorry, green.
Can we use this paper? Absolutely. Can you use white paper? If you don't have this paper, yep. I didn't require you get this in here, right? I just strongly encouraged. Yeah, okay. More questions? Now's your chance. Yeah. Yeah, you can grab a ruler if you want. They're in the boxes. Just bring it back on Thursday. Yeah. Huh? No, you're gonna bring it to me on Thursday. Oh, yeah, it's in Blackboard. Yep. If you have what? I'd do it before Thursday if you have questions. Absolutely. All right, have a good day. Be careful out there. There's still icy spots. Don't find one and then go down and, yeah.
Thank you.